Welcome to Elementary Real Analysis. Today we are going to explore a foundational concept that you will use throughout your mathematics journey, the absolute value. Understanding this simple yet powerful idea is the key to unlocking limits, continuity, and convergence. Let us dive in and see what it is all about. Before we look at any equations, let us think about why we need this concept. Imagine you are standing on a straight road. Whether you walk 3 steps forward or 3 steps backward, the physical distance you have traveled is exactly the same. Distance is a physical quantity that cannot be negative. In mathematics, the absolute value is our way of measuring this exact concept of distance from zero on the number line. It strips away the direction, ignoring whether a number is positive or negative, and tells us only how far away it is from the center. This is why the absolute value of any real number is always zero or a positive number. To define this mathematically, we use a piecewise function, which means the rule changes depending on the number we start with. Let us look at the first piece, which handles the right side of the number line and the center. If our input number, x, is already positive or 0, its absolute value is simply the number itself. The vertical bars around x represent the absolute value operation. So if x is greater than or equal to 0, the distance from 0 is just x. For example, if you move 5 units to the right, your distance is simply 5. As x increases, the distance increases proportionally. Now, what happens if we are on the left side of the number line? This is where students often get confused. If our input number x is negative, we must flip its sign to make the distance positive. We do this by multiplying x by -1. So the formula says the absolute value of x equals minus x. It looks like a negative result, but remember, x is already negative. If x is -5, then minus x means minus -5, which becomes +5. This clever algebraic trick ensures that as x becomes more negative, the physical distance from 0 still increases as a positive quantity. Let us look at this visually on a number line to make it perfectly clear. In the center, we have 0. Notice the point labeled x equals 4 on the right? The bracket shows that its distance from 0 is exactly 4 units. Now look at the left side, at the point x equals -4. The bracket here also shows a distance of 4 units. The absolute value of -4 is 4. The diagram clearly shows that whether you move left or right, the physical length of the path from the origin is identical and strictly positive. Now that we understand the definition, let us use it to solve a basic equation. We are given the equation, the absolute value of x minus 3 equals 5. We are asked to find all real numbers x that satisfy this. Conceptually, the expression inside the bars represents the distance between an unknown number x and the number 3. The equation tells us this distance is exactly 5 units. Because distance can be measured in two directions, x could be 5 units to the right of 3 or 5 units to the left. We must set up two separate cases to find both possible locations. Let us solve the first case, which corresponds to moving to the right on the number line. Here, we assume the expression inside the absolute value is positive, so we just drop the bars. We get x minus 3 equals 5. To isolate our variable x, we simply add 3 to both sides of the equation. This gives us x equals 8. This is our first solution. If you plug 8 back into the original equation, 8 minus 3 is 5, and the absolute value of 5 is indeed 5. This confirms our rightward position. Now we must consider the second case, moving to the left. Here, the inside of the absolute value is negative, so we multiply it by -1, giving minus the quantity x minus 3 equals 5. To make this easier, we multiply both sides by -1, shifting the negative sign to the right side. This gives x minus 3 equals -5.
Adding 3 to both sides isolates x, yielding x equals -2. This is our second solution, representing the exact position on the left. We have successfully found both numbers that satisfy the equation, giving us our final physical locations. We are now ready to introduce one of the most important rules in all of real analysis, the triangle inequality. Why does this matter? Because in advanced mathematics, we constantly need to break apart complicated expressions into smaller, manageable pieces that we can measure individually. The triangle inequality allows us to do exactly that. The core idea is simple. Think of walking from point A to point C. Going directly is always shorter than or equal to taking a detour through some other point B. In terms of numbers, adding them together first and then finding their distance from zero will never give you a bigger result than finding their individual distances first and adding those together. Here is the mathematical form of the triangle inequality. The formula states that the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. Let us break down the symbols. The variables A and B represent any two real numbers. The left side is the distance of their sum from zero. The right side is the sum of their individual distances from zero. If the magnitude of either variable increases, the right side grows proportionally. However, if A and B have opposite signs, increasing one might actually decrease the left side because they cancel each other out. This physical cancellation is exactly why the left side is always less than or equal to the right side. Before we prove why the triangle inequality works, let us see how powerful it is in practice. We are given that the absolute value of x is less than or equal to 2. We are asked to find a maximum possible value, or upper bound, for the complicated expression, the absolute value of x squared minus 4x plus 3. We choose to use the triangle inequality here because it allows us to split this large sum into separate, smaller absolute values. By applying the inequality, we guarantee that the total distance from zero is less than or equal to the sum of the individual distances of each term. Next, we simplify each piece using the multiplicative property, which says the absolute value of a product is the product of the absolute values. The absolute value of x squared is just the absolute value of x squared. For the middle term, we pull out the -4. The absolute value of -4 is simply +4. The absolute value of 3 is just 3. Now our expression is entirely in terms of the absolute value of x. We are given that the maximum allowed value for the absolute value of x is 2. We substitute this number 2 into our expression to find the highest possible total. With the substitutions made, we just perform basic arithmetic. We square the number 2 to get 4. We multiply 4 by 2 to get 8. The constant 3 remains unchanged. Finally, we add these three positive numbers together. 4 plus 8 plus 3 gives us 15. This is our ultimate result. Physically, this means that as long as our input x stays within 2 units of 0, the value of our complicated quadratic expression will never wander further than 15 units away from 0. This bounding technique is a core skill you will use constantly to prove that limits exist. Now that we have seen how useful the triangle inequality is, let us understand why it is true by proving it. We start with a universal truth for all real numbers. Any real number A is always sandwiched between its negative absolute value and its positive absolute value. For example, -3 is between -3 and +3. We write this exact same relationship for our second number, B. Now we have two inequalities pointing in the same direction. In mathematics, we are allowed to add such inequalities together. We add the left sides, the middle parts, and the right sides to create a new combined inequality. This sets the stage for our final result. Let us look at the structure of our combined inequality. On the left side, we factor out the negative sign. Now, the inequality says that the quantity A plus B is sandwiched between the negative version of a sum and the positive version of that same sum. There is a general mathematical rule. If a number y is between minus c and positive c, then the absolute value of y is less than or equal to c. Applying this logical rule to our current step, we immediately get our final result. We have successfully derived the triangle inequality, the engine that drives almost every proof involving convergence. This completes our derivation.
So, we have proven the triangle inequality. But where does this all lead? In real analysis, we constantly talk about things getting close to other things. A sequence converging to a limit means the numbers get closer and closer to a specific target. To define the word close rigorously, we need a precise way to measure distance, and the absolute value provides this exact tool. Without it, we could not define derivatives or integrals properly. Even in the real world, engineers use absolute value to calculate error margins. If a machine part must be 10 centimeters wide with a tiny error margin, absolute value ensures the part is neither too big nor too small, treating both errors equally. Let us review the key takeaways from today. First, the absolute value of a real number is simply its physical distance from zero on the number line, meaning it is always a non-negative value. Second, we learned how to solve equations by splitting them into positive and negative cases. Finally, we explored the triangle inequality, our most critical tool for breaking complex sums into manageable parts, and we proved it from basic principles. You have now covered the full foundation of absolute value. Mastering this is your first major step toward understanding limits and convergence in real analysis. Great job!